All right, let's get started. Yeah. So where were we? Um, Last time I just talked about the previous pointer, so that we're kind of essentially completing the historical game state, like game state representation, discretization, right? I mean, yeah, I talked about it a lot already, but it's almost done. Just the two remaining left is to clone, and then after that we're gonna so it's like if you take a step back, look at the big picture, right? Like we want to implement Alpha Zero for BumperCoins. We've done it with Connect 4. So the first thing you need, in Monte Carlo tree search, you have a game state, right? And then you kind of have a neural network that can take in the game state. So you discretize the game state so that you can represent it as a tensor, and then you pass that into neural network as the input, and then it's going to give you an output, right? So we need a neural network, which has yet to be done, but it's going to be similar, like convolutional, whatever. Like however Connect 4 does it, we'll do something similar to that. So we need to create a network, and then the network will spit out a large array, right? Like a large vector, and then from that, two vectors. Well, there'll be a value head and the policy head. The value head's simple. We just take the value and boom, we're done. But then the policy head, the policies, we need to parse those into a policy, a bunch of moves and weights. So I think we're probably going to work on that stuff right now, just extracting the values, or maybe the network itself, or just thinking about how to do that, I suppose. How to interpret the networked results. Just like the get legal move stuff. Anyways, okay, let's get started. Make sure that my terminal's there. Wait, what am I doing? Not Connect 4. BumperCoins bot. Status. Yeah, I pushed everything. I was looking at game state provider because that's the solution, basically. Let's make this large. No, BIM game state. So right here, you see how we have a clone, right? I realized that rather than doing this by scratch, we can actually copy from BumperCoins. If you look at BumperCoins, game server, game state provider, right? So game state provider actually has a clone function, which I was just looking at earlier, where it takes in a game state and then it spits out, it returns a new game state, which is the same game state. But the only kind of optional thing which it does, aside from cloning it, is it has an optional parameter. Oh wait, I guess it's not optional. It has a parameter where you can you can swap the ownership of coins. Basically if you have your coins on the left side, you can make them on the right side and vice versa. It is a swap between player 1 and player 2. Now the reason why this swap exists actually in BumperCoins is because of rematches. If you have some game state, if you have some initial starting state, some certain configuration of obstacles and coins, then after the game ends, okay, first of all, starting game states are always symmetric, that's a rule. But second of all, some people might have a preference for having their pieces, they like to go left to right or right to left. That's so when you do a rematch, the player 1 and player 2, they're if you're playing BumperCoins, you and someone else, and you're assigned player 1, you get the golden coins and you're player 1. That means they're player 2, they get the silver coins. Now initially I think player 1's, I'm not sure if it's a random or if player 1 starts from the left, but it doesn't matter. The thing is symmetric, so it shouldn't really make a difference in theory. But some players like to play from the left side, other players like to play from the right side. Me personally, I like to play from the left side because I find left to right moves very natural movements for my wrist. That's what I personally prefer. So in the rematch, once the game ends, I don't swap player 1. Player 1 doesn't become player 2 and player 2 doesn't become player 1. The player is tied to the color of the coin, and that's tied to the WebSocket connection. So you're still going to be player 1, but then in the rematch, your coins are going to be flipped. like your coins in the other person's coins are going to be swapped. Obstacles will stay the same. So that's kind of why we have a swap coin ownership. That's it. Rather than like flip the coins, just to relabel them. So it effectively has the same effect of swapping everything. But anyways, the whole point, what I'm saying with all this nonsense is we can just copy this function and just handle that separately. It basically kind of does a deep clone, which we wanted to do. So let's look at it. It takes in a board. It takes in the new game board with a shared constants, whatever. That's like the same thing that's done here. No big deal. In fact, that's copy pasted. It builds up in fresh a new array of coins and wins and obstacles. And then for each of the things we're going to copy, right? Don't worry about this nonsense. It just kind of creates a new coin, and then is P1 Boolean's a primitive? That's fine. We can take the primitive, no big deal. Primitives are it's okay to copy them, but the like the fixed point, like the number itself, is no longer a primitive. It's a custom object. So we have to I have a separate clone method. So we kind of call like this clone, this from game state is kind of a clone, and it in turn recursively clones like these nested objects. So we clone the coordinates, and then again primitive, that's fine. And then we just kind of copy over the actually I just realized ID doesn't even matter anymore. Yeah, do we even have an ID field? I think this might have been like not even matter. I think it does. I think we have an ID field, but we don't need it technically. But I mean, I guess it's just there. Like it's just a relic of BumperCoins. It's not hurting anyone, right? It reminds me of like that. Is that a South Park thing? Like, calm down, Scooter. He's not or Skeeter or someone. He's not hurting anyone. Or I don't want no trouble or something. But anyways. So you have like the wind coin, yeah, same ID stuff, but like, yeah, basically the whole point is that there's fixed point dot clone. That's it, and that's kind of a crucial thing. Like I know like this bug, like initially I forgot that. So as I moved one coin, other coins started moving too after rematch, and I was kind of freaked out, and that's because I forgot to I forgot to like have this clone inside it. And then same thing with wins and obstacles. I mean, oh yeah, we're gonna have an obstacle. I think like. Let's hey, it's that one drawing. Yeah, the obstacle is right. Like we have two obstacles, but the obstacles never change. In fact, one thing I was thinking about like many years ago, I think like when I first conceived of BumperCoins and obstacles, was like coins have health. I was thinking like what if like the obstacles have health too? So if one guy's turtling and just kind of hiding his king behind obstacles, like he's kind of stalling the game like playing Ring Around the Roses or merry-go-round around the obstacles while you're chasing them. What if you can just like kind of attack the obstacle and knock and like kind of destroy it? But anyways, so like what I'm saying is that like if it's mutable, then there might. Okay, I'm going off topic. But anyways, we're just gonna copy this. So let's just do that, right? And then we're gonna get started with neural network stuff, I guess, right? Because ultimately we have to have a neural network, right? Actually, let me just do this one and kind of go from there, right? Exactly. Just join that function right here. What? Oops, two of them. What am I doing? Just like that, right? Actually, no, undo. Just like that. Okay, so clone returns a game state, right? So it starts off with that, coins, wins, obstacles. And then instead of this nonsense like c.isP1 or whatever, it's just a c is p1. Like basically like the swap parameter will always be false. So we always kind of have this case. So let's just kind of do that. That's weird. I mean, this is redundant. Like these two lines should actually have been kind of like this these two lines, like we should have like deleted both of them and just put one outside the for loop. So that's pretty bad technique by me. Oh well. I did all of rematch, all of this swapping code and rematch in literally like less than I think 3 hours in like a library. I just booked a study. Like that's why I said less than 3 hours, because like the maximum time you can book in a study room, at least like in New York Library, like many years ago, is 3 hours. So I remember like kind of just finishing on time, and like I just did the whole rematch code like in just one shot, and everything just worked. So I was pretty pleased with that. But I didn't like it wasn't about elegant code. It was just about getting it done. But yeah. Anyway, so the point is that what's the point? Yeah, the point is that we can just use this, right? Just like that. Okay, so now we have a fresh clone. Now let's just make sure everything compiles. Like now we're actually returning a game state, so that's good. Let's make sure everything compiles or get diff. Yeah, we just added implemented clone. Let's just see if stuff compiles, right? Not.ts. Oh, it's this .coins. It is this .coins, right? So there is a bug. Okay, good. Let me just kind of scroll through again. Board. Okay, that looks good. That looks good, looks good, looks good, looks good, looks good. Looks coin player. Clone the chords. Do that. Okay, fine. Coin. Then this dot win. It's good. So then win whatever. Ah, here's the. Okay, fine. This the obstacles. Okay, good. Okay, yeah, that looks clear. Get status. Let's just do a get add all. Get add. Yeah. Oh, okay. I see the problem. But I had something similar to Connect 4 too. Constructor takes in no arguments, right? Let's just like that, right? Okay, good. No errors. Status. Let me see the format for get log. Okay, so I did capitalize that. Okay, good. Okay, wait, let me check the window. I hear some noise. All right. So right. Time to use the whiteboard, right? Let's refresh, see if you get a new whiteboard. So right now, like we can create a new game state, right? So when we're doing Monte Carlo tree search, we start off with a game state, then like we kind of like we like get a policy, like a bunch of weights for all the actions that like we can take from the game state, all the moves we can make. And then like we kind of like build a tree and like kind of each like we kind of like do that and like we just do tree search on that, right? So that's kind of nice. But so basically like taking a step back, like first thing we need from the game state, we convert this into like the neural network, the net input, like the image stack. Right now we just had vanilla JS, and then we kind of like have it like through the net. We kind of like get like two outputs, the value and a vector. And from this we want to what we want to do is we want to extract policy. It's the get policy and value, right? So like so this step we have to do right here. We have to do this step. We have to create the net. We more or less did this, so we have to convert it to tensor, so we kind of have to do this, like it's almost done, and that's pretty easy. So then main thing is create the net, and yeah. And like kind of put the input, like convert stuff into tensors. The first thing we need obviously for all of this, we need to import TensorFlow, right? So I think we just need to use no GPU, and we don't need like the vanilla TensorFlow, right? TensorFlow JS node GPU. Just reviewing some stuff. Yeah, we have to use like a background worker when I'm in the game BumperCoins, so it's not gonna mess up the UI thread, right? A web worker or something, which I've done before for like the alpha beta thing where I hard coded like those three features: octal distance, like coin health, and octal distance to king, like coin healths, and one more thing. Actually, let me see what Connect 4 does. TensorFlow. TensorFlow, TF.js node GPU. Okay. So we don't have any package.json file. So let's create one. So from 4.15, it became 4.18. Okay. Very nice. It's gonna take too long. I'll end the stream. Okay, perfect. Git status, package. Okay, fine. Let me see my git ignore again. Yeah, we have node modules already in the ignore. That's good. That's good. But yeah, we can see it right here. Yep, we have the TensorFlow. Oh, it has everything. Okay, good. Oh wait, no. Did I already copy and paste that? The net.ts file? Oh no, I don't. Okay, so I'm just gonna copy this line right here. Oh, we have net.ts from that already, from C4. Now it's time to bring in the TensorFlow stuff, right? Let's import TensorFlow, but remember that's not TF.js because we're using the node GPU one, right? Status. I need to make sure it still compiles. Oh, there's an extra I here. I see. That's the problem. I was doing I for insert mode. Okay, great. So now we have our we have TensorFlow in there. So okay, now it's time to build a neural network, right? Time to build a neural network. Actually, I mean, First of all, I'm gonna get some water from the other room. Okay. So right now we have convert that, and like we commented out like the return type tensor, but now let's bring that back up. So first thing, let's kind of finish the game state discretization or representation as a tensor input, right? So let's refresh how it's done in that one. Let's just kind of copy all these things. Okay. So input number array NCHW so like this right here is the image stack, right? Like right now there's no n. Like right now the image stack is just CHW, right? Where like C is the number of channels, H is the height, and then W is the width, right? So like C is the number of channels. So in this case, there are going to be 8 channels. We talked about that, right? Like the image stack has like how many images? Like how tall is the stack? 8. That's how many channels there are. That's analogous to RGB. In fact, we can like kind of visualize this in terms of colors. Actually, wait, no. We need one more we actually need one more dimension for the one more image stack for the obstacles, right? Okay, yeah. Yeah, we actually do need that. We actually do need like an image stack for the obstacles, an image for the obstacles. Even though it's static and will never change, still. Oh wait, no, let obstacle image, which is what? A number, a 2D array of numbers equals this. Paste that. And then what? Like right now it's size 8, because like 4 times 2, right? Game states times 4, like 2 times 4. Game states is 2, by the way. So now we have to kind of do it like we want to just kind of yeah, we also want to encode we want to encode the like here, like we want to encode an image for the obstacles, which never changes because obstacles health is fixed. It's immutable. It's a hard, so like basically all like we have like this height is a 15. That means like 15, and then like each column's height is 15, each row's width is 20, right? So everything like that's 0, 0, everything will be 0 except like the space that's kind of enclosed in the obstacle will be 1, so it's a binary value thing, right? So top left corner is like, well, you can like kind of do it like that, right? So let's kind of like do the same thing here, where like this. Or actually, no. Let's just add a 1 here. Plus 1. Num game states times 4 images, image planes for the coins, and plus 1 for an image for the image plane, image or image, I guess it's image for the obstacles. So then this thing basically kind of populates to all zeros, like to all zeros, like including the obstacle ones. So now what we need to do is we need to get the last one. So like let obstacle image, which is a number, equals the image stack of, how do you do dot length? Okay. Always use length property. Okay. Dot length. So we have this -1, right? -1 to get the last one. That's the last one. And then for let obstacle of game state dot obstacles. Okay, so how do we do this, right? Let let me just open up obstacle. Actually, no, what am I saying? Game state. So we have like 5 and 6, right? 5, so then 2, 3 is pretty clear. That's the x, the y, the width, the height. So the width is 2. 1, 2. That's the width. The height is 3. Okay. So from 5, so that's like the x. 0, 1, 2, 3, 4, no, sorry, 0, 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4, 5, 6. So then the 5 and the 6 specify the top left, right? And then what we have to do for the obstacle is like from here, and then we have the height. So we can do it row by row, either rows, columns. Let's just do rows as convention, right? So for each obstacle, sure, why am I doing this? For let I equals 0, for let I equals 0, I is less than the obstacle dot h for the height. Like we're kind of iterating like 0, 1, 2, like each, like kind of like that. I plus plus. Then let the row its index number equal to the obstacle dot x plus I, right? No, what am I saying? Dot y plus I. right? So like I is gonna range from 0, 1, 2, because the height is 3, right? Like 0, 1, 2. And then like the obstacle's y is 6, right? Yeah, the y right here, or sorry, so what am I saying? That's like the second entry, yeah, 5 and then 6, right? So like 0, 1, 2 is I, then with 6 it becomes 6, 7, 8. So like 0th row, first, second, third, fourth, fifth, and like 6th, 7th, 8th. So like the row index is correct. So that is a row index, that's good. And then we have to do the nested loop, right? Make this J. Instead of height, it's the width. J. So then the image, the obstacle image, obstacle image of the row index. It's indexed into the row. What's this call index? That is going to be obstacle.x plus j, right? I'm just gonna pattern matching on that. Obstacle.x, which is 5. So like 0, 1, 2, 3, 4, 5 to get the offset, and then the range for the j is from 0 and 1. So like 5 and 6. 0, 1, 2, 3, 4, 5, 6. Okay, perfect. Plus j. Simple offsets. Pointers, basic stuff. What am I saying? Equals 1. Just the binary. Okay, so now what I'm going to do here is I'm just going to console.log the image stack of the size of what element? The 8th one. I mean, which is the 9th one, 0 index, to see the obstacle, right? Let's just see the obstacle. I want to see the obstacle. All right, well, let's see the obstacle. Plain status. So what do we do? We just added an extra image for the obstacles, and the obstacle image is like the last one. And then for each of the obstacle, we do the same thing. So that loops for each obstacle. And for each obstacle, what do? We look at the height, and then we do that stack that many rows of the target image, obstacle image, and we set like the valid entries in that row to 1. Perfect. Okay, so let's make sure it compiles. Nope, I failed. Oh, image stack. Okay, I see the problem. Oh, okay. I see that. Already all this change. just like that, right? Okay, so let's see what happens here. For each obstacle, we kind of convert the height to the actual number. And for the row, so the row, we convert the y to the number as the base point for the offset to start. And then similarly, j, we just kind of stick that in. So basically, we add like 4 fixed point to numbers for the height, the width, the x top left, y, the height, the width, the top left y, and the top left x. Okay, so now all the types should be fine. Okay. Okay. So let's look at this. Well, actually, before we look at that, let's look here. We need to see 1, 2, 3, 4, 5, 6 rows of zeros, then 3 of like 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. So we need to see like 3 rows of like 4 ones in them, spaced thusly. So 1, 2, 3, 4, 5, 6 rows zeros. 1, 2, 3, 4, 5, 6 rows zeros, right? 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. So 6 rows zeros, top and bottom. So let's first look at that. 1, correct, all 0. 2, 3, 4, 5, 6. Now something with a 1, something with a 1, something with a 1, and now 6 more zeros. 1, 2, 3, 4, 5, 6. All zeros, correct. 6 plus 3 equals 15, which is correct. 12. 6 plus 6 is 12, plus 3 is 15. There's 15 height. So now it's like they're saying that like these, so everything is 0 except these 3. So like somewhere in like these kind of middle 3 rows, the ones, there's some obstacles. So let's see, like we need 0, 0, 0, 0, like 5 zeros, 2 ones, 1, 2, 3, 4, 5, 6 zeros, 2 ones, 5 zeros. So 1, 2, 3, 4, 5 zeros, correct. 2 for the top row of the first obstacle, good. And then 1, 2, 3, 4, 5, 6. Let me double check that. 1, 2, 3, 4, 5, 6, correct. And 2 more ones, and then all zeros. 2 more ones, all zeros. How many zeros? 5. 1, 2, 3, 4, 5. And if you just look here visually, like the same contours, like it's clear that this one is the same as this one is the same as this one, because there's only 4 ones. These top, like kind of like that, and then like a blank space jutting out for all of them. So that's correct. So then get status. So now we can uncomment out we can just delete that comment for the one we did. Actually, no, wait, before I do that. Let me verify that again. 1, 2, 3, 4, 5, 6. And the same shape 3 times and 6. 6, correct. And 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 5, 6, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, good. Get status. So let's delete this log statement. Get status. Clear. Get diff. We just deleted that. Okay. Get add all. Get status. Okay, great. So now we want to actually like return the tensor, right? Okay. So we copied and pasted, right? Like we like basically like here in the convert game state to model, like this function right here, right? Like this right here is the same thing as our image stack in our code for BumperCoins bot, right? Like we have like a number 2D, right? So like a number 2D, two-dimensional, like one image, like 2D, just call that an image, like an image plane image, right? So then a list of these 2 images is an image stack. So this nested thing is the image stack. So we just have to like, and then so like, so that like by this extra bracket, we kind of like get 3 dimensions, the vertical stack dimension by combining these images, by stacking them. And then there's a final bracket, which is a list of that stack, which just so happens to be 1, size 1. Okay, so let's just kind of take that in mind. right? Where like we kind of an extra wrapping. So now the input of this number array, let's kind of bring that out outside the comment. So this one is a what? Image stack, just like that. Image stack kind of gives us these 3 dimensions, but then there's another dimension which is like the list of image stacks, because like it's the number of these game states, the n, the number, like the batch size or whatever it's called, right? So that's that. And then this is going to be our tensor. And then we're going to transpose it. Wait, yeah, we can just copy these 3 lines as it is. Delete all that. New line. Go back up here. And then what we can do is we can delete this, because and bring back the return type of tf.tensor. Because now what we do is we kind of do that. We just make it a tensor. Then we do a transposition, because like I already talked about this a long stream ago when we did Connect 4. Like NCHW is like what PyTorch uses or whatever, but like TensorFlow like does the transpose where like the n goes at the very end, right? Wait, no, what am I saying? The n is defined. It's always the first argument. It's always 0 axis. But then the C, the channels, it's like goes at the end. Yeah, so like the C kind of goes at the end. HWC. Reminds me of this thing called cycle sort, a sorting algorithm called cycle sort that comes to mind when you think about permutations of like NCHW and NHWC. Like you have like one singleton cycle of the N, and the CHW are like a second cycle, right? Anyways, I'm going off topic here, but yeah, I know I saw cycle sort in some leak code questions. It was pretty interesting. But anyways, well, just thinking about sorting, like what is a permutation, right? Like if you look at like one like kind of source and the destination, and look at how you like do the swaps and the changes, like where each kind of source ends up, like an adjacency graph or something, this matrix. The point is like you kind of like look at like where things end up, like a permutation matrix or whatever, and like see what happens, and like you end up like getting like little, okay, never mind. The point is that like we can just copy this word for word, but the whole point is that like our image stack is the same thing as like the list of those 2 planes, where like here we had like the list of like current player cells, other player cells. Like we kind of programmatically generated like these 2 planes based on like the number of game states using some fancy features and image index thing. Like we kind of dynamically like we didn't like kind of like dynamically generated stuff based on like this number of game states. But yeah, so I think we're done now. So now we have kind of hopefully completed this. I think I used the word hopefully. Let's just copy that. Please compile. Status, clear, get diff. So now, like, rather than like just kind of returning just a void, we're actually returning the tensor. We're actually returning a tensor, which is a suitable input for our neural network, which we have yet to design, but yeah. And then we just kind of do that. Okay, so let's see if it compiles. Yes, okay, compiled. Status, get add all, clear, just want to make it compile again, just because I like seeing no errors. Okay, good. Get status, and then let me just give them get log. Look at the messages. Yeah, hopefully finish. Okay, yeah. So get commit. Hopefully finish. Hopefully finish net dot that. Added obstacles and convert to tensor. Actually, yeah. So the first thing is like the big picture, like we finished this thing, and the actual like meat and potatoes, like what we actually did was we added the obstacles and converted to tensor. Status, now we're 2 ahead of the main, so I think I'll stop for now, and then like next stream we can actually like create a neural network, like convolutional whatever. Again, looking at Connect 4 for inspiration. And then we can, yeah, I think this is a good stopping point now because like we cleanly wrapped up and like got this function to compile at least. I mean, I could do some more tests, but like printing out the tensor and stuff, like tensor.print prints or whatever, and like index into it or whatever. But like I've already done it for Connect 4, and I know this works for Connect 4. It's basically the same thing. We've like printed plain, like we've printed out the actual vanilla JS array list and like array or list, whatever it's called. I think list. We've like printed out all the images in the image stack, including just now the most recent one, the obstacle image. So I'm pretty convinced of the correctness of this. But anyways, the point is that I mean, yeah, the point is that I'm just gonna end the stream because like it's a good stopping point. Very little was done, but I mean, just incremental progress. Like now that this is done, like if you go back to our whiteboard, like this input, like this circle is now kind of undone because like the circle means to do, and like we've now kind of cleaned this. It's so just so happens with the last thing, so undo does it. So now what's left is actually create the net, and then kind of implement the get policy value thing, extract the output and like parse the output into a like remove the illegal moves and like and renormalize the softmax, like renormalize it after filtering out the illegal moves, and then getting a policy vector of like moves and weights, and that's like this thing right here, vector extract policy. Okay, this one of these circles. The point is that we have to create the net and then we have to extract the policy from it. I guess vector. Sorry. Whatever. Like the point is that like this is done, and now we have to now from a game state we can get a tensor, which is the input for the net, and now I have to create the net and like kind of get the net. Like the point is that like we need a net. Like we have taken our game state and we have discretized it to get like a good representation of the game state, an approximate representation of our game state, which is a suitable neural net, suitable input to our neural net, which we're going to create next time. So yeah, we're actually almost done. Like, I think that this is a big, like, getting input is correct. And we have to build the net and handle the output, like parse it, take the net's output and build a policy from that. Like the net.get policy and value function. We have to kind of bring that over from Connect 4, and then I think we're mostly done. Then actually start training. So yeah, I mean, like creating the input is like a pretty big steps, and I feel that like we're either done or on the verge of being done for that part, or I think I just finished it just now. So yeah, basically I'll stop for now.